good day. So, in this lecture we will continue our discussion about Ethernet. In the previous lecture we have already seen the basic data link protocol which is used in Ethernet. Okay. But of course, as I mentioned in the last lecture, that Ethernet is a very popular and nowadays it is almost ubiquitous in the LAN area. So, it is a very widely used system, and the system has evolved, okay, from whatever was the approach to Ethernet in the earlier days and the basic Ethernet protocol that we had discussed. Okay. People are sort of shifting away from it, because as the technology develops and as things like switches etc. become cheaper and as the speed of network goes up, okay, there is a slight shift in emphasis in modern Ethernet. So, in this lecture what we are going to do is that first of all we are going to have a look at the physical layer of the Ethernet. There is not much to discuss over there, and then we will see that how we are shifting from a shared medium to a switched Ethernet kind of concept, and how speed is increasing, and then a little bit about what Ethernet LAN as a concept, we will talk about it. So, today our main discussion is that Ethernet, the modern Ethernet, that means the how Ethernet has evolved, but before we go into that we will look at the topology and some of the limitations of the earlier versions of Ethernet. Now, the topology of a network refers to the pattern of workstations, cables and repeaters. In an Ethernet there are two primary limitations to the topology: transmission accuracy and end-to-end transmission time. So, the transmission accuracy means if you remember that Ethernet really the data link layer is an unreliable protocol, in the sense that it does not do a lot of acknowledgement or negative acknowledgement and things like that. Essentially the transmission accuracy should be fairly tolerable, okay. And what happens is that the maximum distance for accurate transmission is determined by signal attenuation along the cable, and the signal attenuation along the cable would also depend on the first of all on the quality of the cable, the kind of cable you use, and the data rate. The other important point is the end-to-end transmission time. As we have seen that because of this collision and other things, this end-to-end transmission time is important. It is not just for the data rate or things to move faster, but for other reasons also this end-to-end transmission time is a factor. Now, these are the Ethernet physical layer standards that we have. I mean, I mentioned some of them, there are actually more. Okay. So, 10 base 5, so it is 10 megabits per second baseband transmission, and 500, this 5 stands for 500 meter cable length. We mentioned this before. So, this is a so called thick Ethernet or thick coaxial cables, and this has sort of become obsolete now. Then 10 base 2, it is a 10 megabits per second baseband transmission. Once again, all of these are baseband transmissions, okay. That means you do not modulate them to a higher channel, higher frequency channel. So, 10 Mbps, and 2 for 200 meter, about 200 meter cable length, 180 200. Then 10 base T, this again is for 10 megabits per second baseband transmission, which uses UTP cable, the various versions of UTP cable like UTP category 3, 4, 5 etc. And 100 base TX, 100 megabits per second baseband transmission, once again it uses UTP cable. So, these are the maximum segment length. As you see, 10 base 5 is 500 meter, 2 is 185 meters, 10 base T is 100 meters. Fiber optic cable 10 base F or 10 base FL, this goes up to 2 kilometer, alright. But actually the 10 base F is also not in much use these days, because by the time the fiber optic components etc. became cheap and available etc., by that time people have really moved from this 10 megabits per second rate to the 100 megabits per second rate. So, 10 base FL is rather rare now, but we mentioned this anyway. The point is that it's a fiber optic cable, it goes much longer than your copper cables, and it is best between buildings. Okay. So, between buildings, that means where it is going through some open space, etc., we always like to avoid copper because of electrical interference, etc., and all kinds of other problem, and not to mention the distance. So, there fiber is used, and the nodes per segment and in 10 base f could also be more. Okay. This also we will come back to this nodes per segment business later on, as we have seen that previously in 10 base 5 and 10 base 2 there are quite a bit of limitations. For example, in 10 base 2 you see the figure of 30, alright, and a network segment having only 30 nodes is a constraint these days now, where all kinds of things are being networked. Okay. Now, but just for completeness sake, I will just make a quick mention of this 10 base 2 and other kind of technology, although as I said that these have become obsolete now. So, 10 megabits per second, under 200 meters maximum cable length. It is a thin coaxial cable in a bus topology. So, this is a classical bus topology. Repeaters used to connect up to multiple segments. Repeater repeats bits it hears on one interface to the other interface. So, this is a physical layer device just for amplification, strengthening the signal, that is all. So, this is a figure of how they were connected. You have this thin cable. So, this is the thin coaxial cable which has terminator on both the ends, and these nodes should be connected using some T connectors over here, and this is the let us say the network adapter, alright. And when a network adapter pushes some signal onto the cable, the transmitted packet travels in both the directions, alright. Okay. So, this is just one mention about 10 base 5 because connecting a 10 base 5 was more cumbersome than connecting a 10 base 2, although the 10 base 2 connection would get loose quite often in the earlier days. But anyway, this is a 10 base 5, that is a fat thick coaxial cable, the transceiver and the transceiver drop cable, and there will be a network interface card here with its MAC unit and protocol control firmware, etc. So, as I said that this has become obsolete now. Now, let us just talk a little bit about repeaters. Repeaters, you know, we have mentioned that this is a physical layer kind of device which regenerate the signal, provide more flexibility in network design because it depends on where you want to extend your LAN. So, if you want to extend your LAN in some direction, so you may run into this distance limitation of this 200 meter for 10 base 2, etc. So, you may sort of increase that by just putting another segment on the other side of the repeater, okay, so that you can go another 200 meters. So, extend the distance over which a signal may travel down a cable. An example of a repeater is Ethernet hub, alright. So, a hub actually has two purposes. One is to provide a collision domain and replace the cable. We will talk about it when we talk about 10 base T and 100 base T. The other function of the hub is this repeater function, that means it regenerates the signal. So, so this connects together or a repeater or a hub, it connects together one or more Ethernet cable segments of any media type. If an Ethernet segment were allowed to exceed the maximum length or the maximum number of attached systems to the segment, the signal quality would deteriorate. So, you can see that you have one cable segment 1 here, okay, maybe this goes up to its maximum distance. There is a cable segment 2 again going up to the maximum distance, but we put this repeater in between so that we can increase the total distance that may be covered. So, these are the different computers connected to the cable. So, used between a pair of segments. So, this is a simple repeater used between a pair of segments, provide signal amplification and regeneration to restore a good signal level before sending it from one cable segment to another. Now, hubs are essentially physical layer repeaters, bits coming in one link go out all the other links, no frame buffering, no CSMACD at hub, adapters detect the collision, provides net management functionality. So, which means that this hub, although this is an active device in the sense that it has got some electronics in it, but in its action it is more passive. Its active component is restricted to the fact that it regenerates the signal, it amplifies the signal and regenerates it. But so far as the other intelligence is concerned, like detecting collisions and things like that, it does nothing like that. Two signals coming at two different ports of the hub, if they come to the hub at the same point of time, they will going to collide. So, in a sense, a hub is sort of, this whole coaxial cable has been collapsed into one collision domain inside the hub. You could look at it that way. But it does provide some net management functionality. So that means if you have a managed hub, there are two kinds of devices, and we will come back to this topic when we talk about network management. But just to mention it here, the point is that a network is usually a sort of geographically distributed, dispersed kind of entity, but this which has to be managed. So, if there is a problem somewhere, that means, I mean, how would you detect it? Well, maybe some user has put in a complaint. So, what you would like to do is that there are so many things, which connect from the user to the central network. Okay, there are cables, there are maybe switches, maybe hubs, and maybe all kinds of things. So, it is important that you should be able to remotely tell whether or not some active device is functioning. You cannot do this on passive things like cables and all, but there are managed switches and managed hubs, etc., whom a central network station may sort of interrogate and find out whether its health is alright or not. So, if you have a managed hub, you have a net management functionality. Of course, the managed hubs are most costly than unmanaged hubs, etc. So, this is just to show you a picture of a hub. There is nothing over here. So, you see that cable, this coaxial cable coming in here, and this is a T joint, and this T joint is feeding into the hub. Okay, there may be a number of such ports and a number of such things may be connected together. Number of such segments may be connected together. Now, we come to 10 base T, and so far as the physical part is concerned, this 10 base T can go on to become 100 base T, that means from 10 megabits per second we can go to 100 megabits per second, but this T for twisted pair cable, that is UTP unshielded twisted pair cable of various categories 5, 3, 4, 5, etc., they are the dominant physical medium and the varying technology today, okay, for local area networks. So, you can have category 5 cable data transmission up to 100 Mbps, and actually you can go a little bit somewhat more on this depending on the distance. The impedance of UTP cable is about 100 ohm, give or take another 15 ohms over the useful frequency range of the cable. The transmission speed is say about 0.6 to 0.65 multiplied by C. So, it is about 2 into 10 to the power 8 meters per second. Time delay is about 5 nanoseconds per meter. Okay. So, here you can see, I mean, you see there are some 10 base T repeaters and then 10 base FL, 10 base FL segments. FL, if you remember, is for fiber optic cables. This is just to give you an idea about the various delays which are involved. Okay. So, first segment delay is about 0.57 microseconds for this 100 meter segment. Middle segment delay is about 10 microseconds, and here you have a delay of about 0.57 microseconds. The transceiver delay is about 7 microseconds. FL repeated delay is about 1.7 microseconds. 10 base T repeated delay is about 21 microseconds, and so on, and all these delays really add up, and you have some limit on this in order for your CSMACD to work properly. We have seen that. So, this is just the same data in a tabular form. So, you have these various types of categories of cable, these are all other fiber optic kind of cable which go up to 2 kilometers or 1 kilometer. These are sort of obsolete now, and these are the maximum length, and these are the delays, the receiver delay and the delay at the repeater and so on. Now, as I said that what happened was that people moved as the demand for bandwidth grew. So, at least in the LAN it moved much faster than WAN, because LAN bandwidth became quite cheap, and everybody wanted to move from 10 megabits per second to the next speed, which is the 100 megabits per second, and this was called fast Ethernet. So, the fast Ethernet, one thing was that one thing is that when we came to fast Ethernet, this coaxial cable really was out, okay, and so the thing which was preferred was this this unshielded twisted pair or UTP. Category 5 is preferred for 100 megabits per second operation, although category 4 would also work, and there is a way how to connect it. We will not go into all the details, but it is possible to transmit it over category 4 cables also, but category 5 are preferred. Now, one thing about these unshielded twisted pair cables are, because they are used for connection from end to end, unlike the coaxial cables. Coaxial cable, we have seen that there is one cable and many nodes may be connected at intermediate points, okay. That is not done, never done with this UTP cable. UTP cable, on the one end you put a connector, usually an RJ45 kind of connector on the two ends, and then go into two nodes. It is simple as that. So, if there are no nodes in between, just two endpoint connections, where is the so this part of it, this part of the medium at least is not shared. So, one end of course we understand maybe is the computer. Where is the other end? Well, the other end might go into, well, first of all it might go into another machine straight away. So, this is just two machines networked together. More usually, say the other end would go to a network device, let us say to start with it might go into a hub. So, if it go into a hub, so we are talking about not a 10 megabits per second hub, but we are talking about a 100 megabits per second hub. So, it could go into a hub. So, all the nodes which are connecting, that means which are a part of the network, all of them are connected by this UTP cable to this central hub. So, the central hub now is my shared medium and the collision domain, okay. But so far as the UTP part is concerned, there is no collision. So, it might so the cable which was just as we had 10 base T which supported 10 megabits per second, maybe with the same kind of cable, with this UTP cable we could support fast Ethernet, that is 100 base T, but there were 100 base TX. Now, but there is some problem about this. One is that to increase to 100 megabits per second, you see that we have got one order of magnitude jump in the speed, okay. That is not a mean achievement on the same medium, okay. And you know that depending on the quality of the medium, as the speed goes up, its performance tends to decrease. So, there is only, depending on what kind of medium it is, there is only a certain amount of bandwidth, certain kind of bandwidth in a certain range that you can support on that medium. So, to increase 100 to 100 Mbps, different encoding is used to reduce the bandwidth of the transmission. Encoding data at 100 Mbps using Manchester encoding would create a bit stream of 200 Mbps. So, you cannot use straight away Manchester encoding here, because this for this supporting this 200 Mbps, which would require at least 100 megahertz of analog bandwidth, okay, which is too much. Category 5 UTP cable is rated up to 100 megahertz, all right, but for keeping some margin etc., but transmitting a signal of 100 megahertz bandwidth would be unreliable. So, what we do is that instead of Manchester encoding, we go to a different kind of encoding, which is called multi-level or multiple level encoding. To reduce the bandwidth, different encoding scheme is required. 100 base TX uses a multiple level encoding scheme, that is MLT, let us say MLT 3, that is multiple level transition 3. Bandwidth required in this case has come down quite sharply to 31.25 megahertz. The encoding is somewhat like this, say 0 there is no transition, and 1 there is a transition, and this transition could be of various types depending on how the depending on the context. From low, it could be from low to 0, high to 0, 0 to low, or 0 to high, okay, depending on the context. Just we can see this example over here. For example, this is 1011000110. This is what is being encoded. Suppose with a 1 there is a transition. Now we have a transition from 0 to low, that is 0 to low level. Then for 0 there is no transition. After 0 there is a 1. Now there is a transition. Since we are at low, now the only place to go to is high, so we go to a high, and then there is another 1, and since we are going high, we go high some more, so that is another 1, so this goes from 0 to high. Then 3 zeros, there is no transition at all. Then from 0 to 1, now from high, since the 1 has come, you have to come to low, and again another 1 has come, you are going in the downward direction, so we continue from 0 to low, and then another 1 from low to high, and then 0, there is no transition. So this is the way MLT encodes using different levels, multiple levels of signal. This reduces the net analog bandwidth requirement for the cable. So this is how a tenfold increase in the speed was achieved on the same physical infrastructure. So bandwidth required for MLT is half the bandwidth required for a 2-level scheme. Half is of course sort of a rough figure, alright. Long stream of zeros will cause the line to hold a constant voltage and lose clocking. So synchronization so necessary to read the signal. So this is one problem which is handled in various ways, so we will not go into the details of that. One way is to encode each 4-bit sequence as a 5-bit pattern, 4B 5B encoding. In this 4B 5B encoding, so what is done is that instead of a 4-bit sequence, we introduce a 5-bit sequence, so that we get some transition and we can hold on to our synchronization. So this pushes up the bit rate to 125 Mbps for 100 base TX data is only 125 Mbps by 4, which is 31.25 megahertz. Category 3 or 4 cable for a rate of 100 Mbps by using all 4 twisted pairs in the UTP cable. So this is also possible. 3 pairs will transmit data, while the 4th pair is used by each station for collision. As in 10 base TX, a 3-level signal is transmitted in 100 base T4. T4 is when you are using category 4 cable, but the data rate must be minimized further. Therefore, the signal is broken into 8-bit sequence, and each 8-bit sequence is represented as 6 3-level signals. So B8, B60. So we need not much bother about it. Actually, if you are going to put in a new network today, you are never going to use category 4 UTP. You are always going to use category 5 or better today. Alright, as you know, because you know about the increasing requirement of speed in the LAN. But these techniques were developed so that Ethernet could move into some existing physical infrastructure, like so some existing wiring is already there using maybe say category 4 cable. So you use that from moving from 10 to 100 megabits per second. So that is why these were developed. So fast Ethernet, so these are some of the these things, 100 base T4 with category 5, 100 base TX and 100 base FX. This is quite common. As I said, 10 base FL has become outdated, but 100 base FX is still there, which uses fiber optics, goes up to 2 kilometer. These go up to this category 5 UTP goes only up to 100 meter, or maybe some people are conservative and limit it to only 75 meters. So it works at full duplex at 100 Mbps, fiber is again full duplex at 100 Mbps. These are the advantages. The advantages of T4 is that it uses existing category 3 UTP if that is already there and you want to use that. Okay. So, these are the repeated delays of that, we need not bother. So, 10 base T and 100 base Tx varying, as I said that the varying goes like this, that from the end station. So, 100 meters maximum distance hub to station can use multiple hubs, maximum 4, to increase the distance between any two stations. So, a hub may go to another hub, that may go to again a station. So, that way so now there are 3 segments. So, you can use maximum 4 hubs and 5 segments with 100 meter from the node to the hub. So, upgrade from 10 base to 100 base Tx. So, what you need is you need new hubs and switches, may have some 10 Mbps ports to handle 10 base T NICs, may have auto sensing 10/100 ports that handle either. Okay. And these auto sensing ports are quite common. As a matter of fact, most of the network interface cards that you get today they are 10/100, that means auto sensing ports. So, so that it will sense what is the network device which is there on the other end. If that other end supports a rate of 100 Mbps, then this NIC will operate at 100 Mbps. If it senses that the opposing end can handle only 10 Mbps, then it will use only 10 Mbps. By the way, if there are problems with the varying connection etc., it may sense a 100 Mbps port as a 10 Mbps, that is just a small point. So, if you want to upgrade from 10 base T to 100 base Tx, you may need new NICs, and only for stations that need more speed and no need to rewire. That may be a big advantage in some cases. As I said that you may have multiple hubs, one connecting to the other and 4 of them in this thing. So, you can have multiple hubs for connecting etc. In 100 base Tx, of course, there is a limitation that you can have only maximum 2 hubs and they must be within a few meters of each other. So, the maximum span using these hubs is a only 200 meters, which is shorter than 10 base T. That of course could be a big problem. So, it is not done this way. Actually 100 Mbps hubs are also becoming obsolete, you know that in this field of networking things become obsolete very fast. So, 100 because primarily because of this limitation and other sort of limitations of hubs in general. So, 100 as things move to 100 Mbps, people also slowly migrated from hubs to switches, and that is what we will be talking about. So, if you had used hubs, this would be the limitation, but as a matter of fact nowadays people do not usually use hubs. And then the development, so we will come back to this topic about hubs and switches later on, but what happened is that this development went on and now we are moving into the era of Gigabit Ethernet, alright. So, Gigabit Ethernet in the desktop is still not very common, but it is coming, and we are sure that at least for servers etc., nowadays we routinely get gigabit ports, and maybe soon your desktop computer may also be connected with gigabit ports. So, this is an depiction of a 2 station Ethernet, 2 computers connected straight away. This is a switch or a hub which operates at gigabit speed. So, these allows point to point links and shared broadcast channels through some hubs if they are there. In shared mode, CSMA/CD is used, short distance between the nodes to be efficient, but this is not very common. Now, what are the specialities of Gigabit Ethernet? It uses standard Ethernet frame format 802.3Z. The normal mode is full duplex mode with a central switch. So, this is the most common one, connected to computers. In this configuration all lines are buffered, alright. So, if you look at this, so maybe if you forget about this let us say this right hand side. So, one switch and nodes connected straight to the switch. So, this is a switch rather than a hub, where each of the port has a buffer in it. So, since each of the port is a buffer, so contention is impossible. Because it can always the data can always travel and get sit on the buffer. So, no sense the channel to see if it is idle or not, because if there is no contention, then you need not sense or do anything at all. Okay. CSMA CDS protocol is not used at all, and this is the mode in which gigabit is usually used, although there is a shared this thing also, which are buffered distributors using hubs. And now people are talking about moving to 10 gigabits per second, at least in the metropolitan area network. Okay. This of course would use copper and fiber with this kind of with 850 nanometer or 1300 nanometer lasers and some kind of encoding. So, we will not get into the details of that. So, you can see that Ethernet is really moving, that is because it is I mean it is upgrading quite fast, I must say. So, from 10 Mbps we went to 100 Mbps, from 100 Mbps we are moving to 1 Gbps, and from 1 Gbps we can sort of seeing the possibility of moving to 10 Gbps. As a matter of fact, sometimes 10 Gbps gears are already are in operation today. So, that is from 10 Mbps to 10 gigabits per second, that is a 1000-fold increase in a very short span of time, which is really amazing. So, for gigabit Ethernet we have 1000 base SX. So, this SX shows a multimode fiber for a 1000 base. So, the maximum segment size would be about 550 meter. 1000 base LX, this uses single or multi-mode. So, this goes 5000 meters. Shielded twisted pair would only take you to 25 meters, and 1000 base T you can go up to 100 meters using category 5, category 5E, or for gigabit Ethernet actually category 6 is preferred. We discussed this when we were talking about the physical medium in the beginning of our lecture series. Okay. So, now we will talk more in detail about the switching business, which is very important. So, Ethernet is a usually was conceived as a shared media LAN, only one station can transmit at a time. Even when you have multiple hubs, these hubs are all shared domain, which means that only one can transmit, others all other stations must wait. One station sends, all other stations must wait. Okay. So, this is the big limitation of latency and congestion with hubs. So, to improve this, people moved over from hubs to switches, packet switches actually, as we have talked about packet switches before. So, this is how, and this is where they are very useful. It gives you improved security. Users are less able to tap into others users data. In a shared medium, you know, everything is being broadcast. So, all packets are going to every other node. So, so that is very poor security really. So, this gives you much better security. Better management, control who receives what information. That means, even using a switch, even within a LAN, you can make some work group kinds of things and make them members of different virtual LANs, and these virtual LANs I mean there may be packet filtering between the virtual LANs, etc. So, that will give you better management. Limit the impact of network problems. This switch is also give you full duplex communication rather than half duplex, alright. One thing I mean one side effect of having a shared medium where only one sends and others everybody else is in the receiving mode, there obviously the channel cannot work as a full duplex mode anyway, because two of them cannot send simultaneously at the same time, only one may be sending and then the other may send. So, this is at most this works as a half duplex channel, whereas over here this can work as a full duplex channel. So, that is again very good. So, hub simulates a single shared medium, whereas switch simulates a bridged LAN. We will talk about the details of bridges later on in the next lecture, with one computer per segment. That means, it is as if you have only one computer, there are so many segments, and there is only one computer for each segment. So, it does not have to bother about any collision, and then from two different computers you can send data at the same time to the switch maybe will buffer it, etc., and then sort of, so there will be no collision. So, collision detection, etc., may be eliminated. Of course, some of these, instead of going to a computer, some of these may connect to a hub. So, a switch may connect to another switch, that switch may connect to a hub, and that hub may connect to so many computers, etc. So, there are so many possibilities. So, Ethernet switches, one good thing about this is that they are highly scalable. We had 10 base, originally we went from 10 base T hubs to 10 base T switches. 10 base T switches are sort of increasingly being replaced by 100 base TX switches with auto sensing ports. 100 base TX switches are very common these days, so have higher performance and their cost has really come down quite a lot. Okay. So, you get a 100 base TX switch these days at the cost of what a 10 base T hub would cost just a few years ago. Alright. So, you can see how the technology has improved and the economics has also improved. Gigabit Ethernet switches, of course, are still expensive. Okay. So, Gigabit Ethernet, in order to move to the desktop, it will take some more time. So, the other advantages of switches is that there are no limit on the number of Ethernet switches between the farthest station. So, no distance limit on size of switched networks. You remember that when we were talking about 100 base TX and when we were using only 100 base TX hubs, you can have only maximum of 2 hubs, and then these 2 hubs have to be close together. Okay, they cannot go far long. So, the maximum span of a network, local area network, could at most be 200 meters, which was really a limitation. But then people, when they moved to 100 base TX, they also moved from hubs to switches, and with switches now there is no problem, because this distance limitation, etc., had to do with the round trip propagation delay and things like that. But since there is no contention and the switches have buffers, so there is no distance limitation at all. So, you can have any number of switches connected to each other. So, there is no distance limit on size of switched networks. So, often individual hosts are connected into switch, and then maybe different switches are also connected, that could also happen. So, it is Ethernet, but no collisions, no CSMACD. So, this is just often this is this thing. So, we have this A, B, C, D. So, now suppose A wants to communicate with A dashed and B wants to communicate with B dashed. Now, both the communications may take place simultaneously. This is a switch. This, had this been a hub, that would not be possible, but since this is a switch, B can communicate to B dashed and A can communicate to A dashed. And just as in a telephone switch, two pairs of distinct pairs of peoples can communicate at the same time, similarly two distinct pairs of machines through this packet switch can communicate at the same time. So, this is essentially a multi-interface bridge. So, layer 2 frame forwarding filtering using LAN addresses. LAN addresses means the MAC addresses. We will talk more about, we have already mentioned about MAC addresses, we will talk more about it presently. And switching A to A dashed and B to B dashed simultaneously, but no collisions, and this can have a large number of interfaces. A modern switch may have hundreds of ports, alright. So, hundreds of machines can be connected to the same switch. Similarly, a number of such switches can connect to each other. So, Ethernet switches must be arranged in a hierarchy or daisy chain. Only one possible path between any two stations. So, you have, suppose from 4 to 3 there is only a single path 4 to 1 3, alright. That is how it is. So, you do not make a loop connecting 2 ports of a switch, that would really create a lot of problem. So, Ethernet switches must be arranged in a hierarchy or daisy chain, only one possible path between any two stations or switches. So, a station is an Ethernet frame switch plug-in card. So, contains so it checks to see if it is destined to the same card. If so, the frame is copied there. Okay. You remember when we were talking about packet switches, we mentioned that in a packet switch usually the ports would be grouped into somewhat into small groups, and each of these group would go into a particular line card. Okay. So, this line card is there. So, similar thing. So, since this is Ethernet switch is nothing but a packet switch. So, there will be line cards over there, and maybe let us say there are 4 lines coming to one particular line card, and maybe there are 8 line cards for a 32 port switch. Okay. Now, those which are coming into the line card, there are various there are variations of how it is handled by the line card. So, that is what we are talking about. So, it could be that a frame which has arrived in a switch plug-in card, so it is destined to the same card, that means it is destined to some other line in the same card. So, if so, the frame is simply copied there. If not, the frame is sent. Now, these line cards should get connected to each other through the back plane. So, the frame is sent over the high speed backbone to the destinations card. So, it will go to the travel to the other this thing through the switching fabric maybe. So, this backplane may be active, passive, there are various types. Anyway, the backbone typically runs at many gigabits per second. As a matter of fact, nowadays it is possible to have a high end switch with maybe something of the order of 100 gigabit per second backplane speed. So, it is a very high speed which can support a lot of machines at the same time. So, if 2 machines attached to the same plug-in card transmits frame at the same time, what would happen? Now, you see, so there are 2 machines attached to the same plug-in card and transmits frames at the same time, depending on. So, what would happen would really depend on the way the card handles it, and here there are some variations. For example, let us say there are 4 line cards 1, 2, 3, 4, and line card that means 4 lines coming into this one particular line card 1, 2, 3, 4, and line 1 and line 2, 2 frames have arrived simultaneously, and both of them are destined to, let us say, line 3. Now, what is going to happen? Now, it depends on how it is handled. One possibility could be all the ports on the card are wired together to form a local on card LAN. So, this line card itself, that is a local on card LAN. On this on card LAN there will be a CSMA/CD network. Okay. So, CSMA/CD may operate on that particular card itself. So, there may be, in that case the same thing will happen, there will be collisions will be detected and things like that. Only one transmission per card is possible at any instant of time. So, if you are doing that, that means you have made that line card to be a shared medium. So, one transmission per card is possible at any instant of time. So, all the cards can be transmitting in parallel. The different cards of course may be transmitting in parallel, that does not matter. Each card forms its own CSMA/CD network independent of the others. So, that is one possibility. The other possibility is that the plug-in card of each input port is buffered. So, incoming frames are stored in the cards on board. So, this allows all input ports to receive or transmit frames at the same time for parallel full duplex operation. So, this is not possible with CSMA/CD on a single channel. So, if there is a buffer on each of the input lines, so previously we had talked about buffers in packet switches. We mentioned that how buffers could be on the input side, how buffers could be on the output side, and then distributed throughout the switch fabric, etc. That was from the point of view of handling head of line blocking, switching speed, etc., etc., etc. Here we are talking about something slightly different, in the sense that if there is some small buffer at each of the port and the input side itself, then full duplex transmission at the same time are possible on all the lines. Okay. Instead of making a local CSMA/CD and allowing some kind of what do you say, collision etc. over there. So, this naturally is a better kind of switch. So, once a frame has been completely received, the card can then check to see if the frame is destined for another port on the same card or for a distant port. In the A case, it can be transmitted directly to the destination. In the B case, it must be transmitted over the backbone to the proper card. Each port is a separate CSMA/CD, so collisions do not occur. Okay. So, there is now no question of any CSMA/CD because each port has only one machine. Then there is another term called cut through switching. frame forwarded from input to output port without awaiting for assembly of the entire frame. That means, even when the frame is not fully has come in, but the bits are transmitted. So, this there is a slight reduction in latency. So, combinations of shared dedicated 10, 100, 1000 Mbps interfaces, these are possible. So, on the same switch you might get some 10 Mbps ports, some 100 Mbps ports, even some 1000 Mbps or gigabit ports for uplinking and things like that, for uplinking to the main backbone and things like that. So, this is a typical LAN of an IP network. So, let us just have a look at this figure. So, let us say we still some hubs are remaining, but as I said that these hubs will give way to switches and from 10 base T to 100 base T very soon, but let us say these are some legacy systems with some 10 base T hubs and some computers connected to these. Now, these hubs may be connected to a switch. Well, this switch could be connected to another switch and that switch might connect to some other nodes, etc. So, this constitutes the LAN. Maybe there is a 100 Mbps connection from this switch to the mail server, because mail server may be something which everybody is using. So, this is a server. So, you might want to have a higher speed on this one also. So, these are, although these are 10 Mbps ports, this you want to make it 100 Mbps. There is a www server that is web server which is also connected through a 100 Mbps port. So, from the same switch we may connect to some hubs, we may connect to some servers, we may connect to some individual desktop PCs or machines or whatever it is, etc. So, this is what the LAN part looks like, and of course, nowadays nobody would want a LAN which is just standing by itself. So, people want to connect their LANs to the so called internet, which is the great network of networks. So, we will talk about internet later, and but for if this is one network, maybe there is some other lots of other networks, maybe millions of other networks in other places, we want to connect to other networks also. So, we have to go through what is known as a router. So, we go through a router to the external internet. So, this part we will be talking about when we talk about the network layer in more detail. So, this is a typical picture of a LAN. If we abstract this a little bit, so we have a LAN and the different nodes or the different machines are connected to this LAN, and then there is a router which connects you to internet. So, this internet of course maybe will be a connection of between a lot of different networks, maybe a lots of different LANs through their own routers, etc., etc. Okay. So, this is a slightly more abstract view, and then looking into it in the detail in the LAN part of it, if you go to the previous picture. So, this is the LAN part of it, these nodes are connected, but how exactly are these nodes connected? Well, these nodes are usually connected through a adapter, that means the network interface card NIC or the adapter. So, these adapters, and as you know that when these adapters, so then these nodes may communicate with each other in the LAN, it may also, if it is connected to the internet, naturally it may communicate with other machines out in the outside world also, but let us for the time being just focus our attention on the nodes which are in the LAN, and they are sort of trying to talk to each other. So, if they are wanting to talk to each other, maybe this is using either it may be using a hub or a switch or whatever, but you know that in this case anyway, as the if you remember the Ethernet frame format, what is going to happen is that if you are putting something, that frame format has got a certain fields, and those fields have to be filled up. That means the destination address has to be there, and the destination address is the LAN address or the MAC address or the hardware address, so called hardware address, the Ethernet address, sometimes it is also called an Ethernet address, and this Ethernet address, if you remember, is distributed by IEEE. Okay, the manufacturers of these adapters, they buy blocks of addresses from IEEE, and these are all 6 byte addresses. So, this is the 6 byte address, something like this 1A 23 F9. So, each of them is a 1 byte. So, you see 1 2 3 4 5 6, And if you look at these figures, say 1A 23 F9 CD 06 9B and 88 B2 2F, so they do not have any relationship with each other, they are just 6 bytes, maybe 6 arbitrary bytes. Okay. So this card may have come from some manufacturer, this card may have come from some other manufacturer, they got entirely different blocks from IEEE, so they got entirely different addresses which have got no relationship with each other, but they are all sharing this LAN, they are all connected in this LAN. So there is a small problem, which is that how does the source node get to know the destination address? One thing is sure, since one central agency, namely IEEE, gives these Ethernet addresses, so each adapter on LAN has unique LAN address. No two adapter will ever have the same address. As a matter of fact, sometimes there may be some nodes with a number of LAN addresses with a number of adapters, etc., but one particular adapter will have one unique address. Two addresses will never be the same, because then you are in trouble. The point is that how do you get to know, this is the source, let us say, and this is the destination. How does the source know the destination's LAN address or the MAC address? I mentioned this before, and I mentioned this again, that there are at least two kinds of addresses which are used in networks. Okay. Actually there are more kinds of addresses, we will talk about the others later on, but at least there are two kinds of address. One is the IP address, so called IP address, which is used by the network layer to decide on the total route from the source to the destination. So what will happen is that it will know that it will have to go via this. So this addresses should have some kind of relationship with geography. And then there are these hardware or MAC addresses which are at a lower level, which are just that they are unique, but they do not have any relationship with each other. So we have these 32-bit IP addresses, network layer addresses used to get datagram to destination IP. We have LAN or MAC or physical or Ethernet or hardware addresses used to get datagram from one interface of another to another physically connected interface in the same network. So this is 48-bit MAC address for most LANs burned in the adapter ROM. So analogy is MAC address is like social security number, IP address is like postal address. Okay. The question is that how do you get to know the other person's address, address translation? How does a host know the MAC address of the other host in his local area network? And secondly, how does a router determine the MAC address from the IP address of a host? So these are two interrelated questions. So we need some kind of a translator for IP addresses from MAC addresses. Address translation can be static or dynamic. Static translation means maybe you keep some static table or something. The static translation requires a lot of bookkeeping work from system administrator, and this is not really feasible, and this is never done. We have this address resolution protocol or automatic resolution protocol, so called ARP protocol, which is a dynamic address translation scheme. If destination IP address is not in local ARP cache, ARP cache is a table which is stored in the local machine, which gives this IP address to MAC address mapping. If it does not know, it broadcast query for that address. At most one host will reply, because only for one host that IP address will match with its own. So the ARP table entries are cached for up to 15 minutes unless if refreshed. Why for only 15 minutes? So that a machine can go away, it can go from one LAN to, it can go be shifted to another LAN. So what will happen is that, so this the old entries must automatically wash out, okay, and the new entries, if they are communicating machines, if they are communicating, their MAC addresses are going to come into the cache. So this is how it is always kept fresh. ARP uses layer 2 broadcasting. So each IP node on LAN has ARP table. ARP table is IP MAC address mapping for some LAN nodes, and there is a time to leave, something like 15 minutes, or it depends, time after which the address mapping will be forgotten, typically around 15, 20, 25 minutes. So starting at A, we want to send datagram address to B, look up the net address of B or link layer. So what is happening is that, what will happen is that I want to from A I want know B's MAC address, that means this 223.1.1.1, this is an IP address, I know his B's IP address, but I want to know his MAC address. So, A's IP address, B's IP address and some IP payload. So, there is a frame like this which is broadcast to the listing. We will look at the details. A wants to send datagram to B and A knows B's IP address. Suppose B's MAC address is not in A's ARP table, A broadcasts ARP query packet containing B's IP address. All machines on LAN receive ARP query. B receives ARP packet, replies to A with B's MAC address. Frame sent to A's MAC address which is unicast. Now, it is now specifically given to A's MAC address because now A's MAC address is known because A sent the query with the source address. A cache saves IP to MAC address pair in its ARP table until information becomes old, that is it times out, but if it is being used then it will not become old. So, soft state information that times out goes away unless refreshed. ARP is plug and play, so you need not bother, otherwise I mean it will get washed out and new entries will come in automatically. Nodes create their ARP table without intervention from the node administrator. All hosts receive the request, but only B responds with the IP address. However, other nodes may update their own cache from the transaction, and the cache is required since broadcast is a very expensive proposition and more than one packet transfer is very likely between any two stations. And this is an important question. What is a network? We always talk about networks. It is the interconnected nodes in the same broadcast domain. So, this you are doing the broadcast. So, this broadcast is limited to that domain. We will come back to this topic later on. Networks are connected through routers. Now, when you want to route to another LAN, that is somewhat more somewhat more involved. So, maybe we have come to the end of our this thing today. So, we will discuss this about talking from one LAN to another in the next class. So, we will talk about going through a router and then we will specifically discuss bridges. Thank you. Good day. So, today we will be talking about local internetworking. So, our topic of today is local internetworking. What is internetworking? Internetworking is connection of different networks. Well, everybody is aware of the term internet today. It really comes from this term internetworking, and by internetworking we means connecting different networks. Just to remind you, what is a network? Well, we discussed this in the last lecture, that the interconnected nodes in the same broadcast domains. Okay. And networks are usually connected through routers, but as we will see, for local internetworking we may not need a router, we may need something called a bridge. We will come to that. So, this is the set of nodes which are in the same broadcast domain. Now, this broadcast may be a good thing to have for some application, but for the operation of the network there is one very crucial reason why we require the broadcast, that is to discover the MAC addresses of the different computers. Okay.